Okay, I guess we'll start. Uh, Hello, greetings, class of STEM 100 and instructor Miss J. We are the Planeteers here to present space exploration. The topics of discussion will be rockets and rocketry by myself, John Medrano, satellite launches and integration by Rachel Baker, satellite communication technologies by Giovanni Venegas, Space Debris Part 1 by John Sunby, Space Debris Part 2 by Moses Akinbowale, and AI and Robotics by Kayla Snyder. Rockets and Rocketry. What do the rockets say after a successful launch? That was a blast. But how does a rocket work? A rocket is a device that channels explosive force to create thrust. Generally, the rocket consists of a fuel or propellant stored in a secure container, usually a cylinder. The cylinder must be open only in one direction so as to let out the explosive force of the fuel when it is ignited. Modern rockets have a nozzle which directs the explosion of the rocket in one direction. You can simplify this by thinking of a rocket as a controlled explosion. What makes up a rocket? The four systems of a rocket are the structural system, which is the frame and form of the rocket, the payload system, the purpose of the mission of the rocket, the guidance system, the brains of the rocket, and the propulsion system, the format in which the rocket gets launched. Rocketry of the past. Greek philosopher and mathematician Archimedes made a pseudo-rocket with a wooden pigeon suspended on wires, propelled by steam. In the early 9th century, Chinese monks developed what we know now as gunpowder. This mixture used saltpeter, potassium nitrate, sulfur, and charcoal. Further down the road, in 1232 CE, the first military use of this mixture created what we know now as fireworks. Their version was called flying fire lances, which was used to deter the invading Mongol Empire. In science fiction, author Jules Verne wrote a piece entertaining the idea of a cannon sending astronauts to the moon in 1965, which is just over a century before the first instance people were sent to the moon on the Apollo 8 mission of 1968. Not to say those real astronauts were launched from a cannon, though Jules Verne's view of space exploration was inspiring to many rocketry engineers and inventors. Rocketry of the present and future. SpaceX's Starship Super Heavy is a two-stage lift launch vehicle. It is the heaviest, tallest, and most powerful space launch vehicle to have flown in space and is intended to be a fully reusable vessel. United Launch Alliance's Vulcan Centaur is a two-stage heavy lift with four standard offering configurations including 0, 2, 4, and 6 solid rocket booster variants. Japan Aerospace Exploration Agency's JAXA H3 aims at achieving three factors: high flexibility, high reliability, and high cost performance. This is Japan's hope for entering the global launch market as a competitive player. And Relativity Space's Terrain R is scheduled to make a debut in 2026. After the unsuccessful launch of the Terrain 1, the experience and data collected to be forwarded to the Terrain R. This launch vehicle will be made by a majority of 3D components. Thank you for your time, and now I'll be moving on to the next presenter.
All right, good evening or afternoon, everybody. My name is Rachel Baker, and I will be presenting on um, the engineering and general science aspect of satellite launches and integration. Next slide, please. Okay, so something important to recognize before we get into the launch part is that there is an actual international telecommunication union. And basically what this is it's an agency controlled by United Nations that provides information on communication technologies. So it consists of approximately 193 countries, and it is based out of Geneva, Switzerland. And their primary focus is to regulate the orbital slots for the satellites. So the main example or main point that I want to get on that is that since there's so many satellites and various other space junk in space right now, we need to be aware of what is in each slot. So this agency allows different countries and organizations to basically allocate a slot for their satellite so that they're not crashing into each other. Next slide. So this agency is pretty pricey. National governments pay an annual fee of $320,000 per unit for their membership. And the United States is the top contributor with 35 units or 11.2 million per year. So next I want to talk about the different orbits that we use. So we have LEO, which is low Earth orbit, and those would consist of the International Space Station, the Hubble telescope, and then other various military satellites. Basically, they're low to the Earth, they're not as high, and they're moving a lot faster. And then you have the MEO satellites, which are primarily the GPS. And you have the geosynchronous orbits, which we call GEOs, and their speed actually matches the Earth's rotation. So if you're on the ground and you're controlling a satellite terminal, what you're going to be doing is just pointing to one specific spot in the sky if you're trying to reach that GEO. And basically the rotation of the Earth will just follow that along. And then last we have HEO, or highly elliptical orbits. And these orbits, basically, they reach an apogee and perigee point. So, for example, if you need communications in the polar region, this satellite is going to go very high above the Earth on the polar region. And then as it comes down, it's basically going to get very close to Antarctica and swing around and basically like blast off and go on from there. But next slide. So next I want to talk about the Starlink satellites and their impact, because this has been a pretty deep conversation lately in politics and science and astronomy. And so since 2019, SpaceX has been launching these small satellites in hopes of providing the entire world with internet. And this would be considered a mega constellation. And currently there are 5,500 small satellites in this LEO orbit, with the number allegedly increasing up to 30,000, which is quite a lot because right now in the sky we have around like 15,000 satellites. So you're adding 30,000 more satellites. It's a big jump. So the controversy comes in from astronomers speaking on the fact that these satellites impede their ability to observe the night sky. And if you go out on a dark night, you can see these Starlink satellites. They look like little like balls of fire kind of following each other. And some people might think they're aliens, but yeah, they're just SpaceX. And then also with the increase in satellites, government agencies have also expressed their concern with the possibility of collisions. And since Starlink is not a federally funded or government program, they are also required to purchase their own membership for their orbital slots through the ITU. Next slide. And now what I'm going to cover on is the general science of space exploration, as well as a little bit of engineering. Next slide. So this mission is a big primary focus for NASA that has been coming up, and it's called the Dragonfly mission. And basically what it is it's a rotorcraft or like a helicopter, and they're going to launch it to Saturn's largest moon, Titan, to explore the diverse environments. So that includes geology, atmosphere, various things like that. So the journey will actually take 7 years. So it will take 7 years from the time it launches to get to Titan. And then once it lands and is properly deployed, upon successful completion of this flight, this will be the second rotorcraft to fly on a celestial body other than Earth. And the total mission is only expected to last for about 32 months, which is kind of crazy to me because it's going to take 7 years to get there. Next slide. So a little background on Titan. It is Saturn's largest moon. It was discovered on March 25th in 1655 by a Dutch astronomer named Christian Huygens. And one day on Titan is equal to 16 Earth days, TESOL being the correct term. It is primarily water ice dominant, and it is very cold, negative 290 degrees Fahrenheit, but it is very abundant in carbon-rich chemistry, sorry. Next slide. And so that's a picture of what it is expected to look like. Of course, it's still in the building phase, but it will have 8 rotors. The spacecraft will fly like a drone in Titan's dense environment, and the flights will last for approximately 30 minutes, and they should cover 10 miles of distance at each time. Titan's condition are very similar to those of an ultralight aircraft on Earth, and the Dragonfly's flights will be fully autonomous, meaning that it needs to be able to function without basically personnel controlling it on Earth. Next slide. And then just to touch on the engineering aspect of it. So some of the instruments include the Dragomet, which is designed to perform pre-flight checks, such as measuring atmospheric properties and wind. And that's very important because they're only going to have one of these over there. It took 7 years to get there. If you're going to launch this thing and the wind is too high, then you're throwing away millions of billions of dollars if it gets damaged. It will only fly under clear weather conditions to ensure the safety and longevity. And then some other instruments that will be included on it will be cameras, radar, ultrasonic, altimeter, and LiDAR technology. And LiDAR is actually the same technology that our robotic vacuums use in our home. So Sharks or any other kind of vacuum like that, they basically bounce lasers off of the environment around them, and that's how they are able to find their way around. So I think that's pretty cool, and I look forward to seeing what they discover once they launch this and get this going. And I believe that is it for me.
Testing, testing, 1, 2, 3.
I
Test.
can hear you.
Thank you. I do apologize for that. My portion of the presentation today is about artificial intelligence and robotics. Um, I've entitled my portion as the real MVPs of space exploration because while researching this topic, I realized that artificial intelligence and robotics both play a huge, huge role in space exploration. Slide, please. So the first thing, I do sincerely apologize for my voice. I currently have bronchitis and I can't really help that. But I'm going to do my best to answer a couple of questions for you. The main questions that we're going to talk about is what role do each of them, that is both AI and robotics, what role do they play in the process of space exploration? And then we're also going to try to talk about how these roles relate when it comes to STEM disciplines. I'm going to do a brief overview of we'll do a brief overview of several different kinds of spacecraft, and we'll learn about a few real-life examples of spacecraft. I will also be mentioning a few different space exploration authorities throughout the presentation, but I'll be doing that throughout different slides instead of all at once. And then after that, we'll discuss kind of the main points, the robotics and AI specific roles in the field of space exploration, and then we will wrap it up. Slide, please. So there are quite a few different kinds of spacecraft that I've listed on this slide, but this is definitely not a comprehensive list. Regardless, most, if not all, of the spacecraft vehicles on this list are significantly affected by AI and robotics at either some or even multiple points in the overall process of space exploration. On the following slides, I've listed some real-life examples, specifically a humanoid robot, an autonomous robotic system, and a Mars rover. Slide, please. So first up, we've got Valkyrie. She was designed by a team at NASA. When she was designed, she was with high dexterity and the ability to withstand harsher environments. She is currently Earthbound, but she has proven to be successful in her aim so far in testing environments. And this enables her to basically go into environments that humans couldn't enter due to danger. Next up, we have Caesar from the DLR, or the German Aerospace Center. Caesar is very, very useful, capable of several servicing tasks, including catching satellites. Rachel explained the difference between LEO and GEO orbits in her portion of the presentation, and that's relevant here because Caesar can actually catch satellites in either LEO and GEO, and he also functions autonomously, making him a highly valuable agent in the process of space exploration. Slide, please. So next up, we have Perseverance, an amazing little rover. Perseverance is a Mars rover and has withstood the harsh environment of the red planet for 1,000 days as of December 12th of this year. The first image is Perseverance in a cold testing environment. And in the second image, Perseverance takes a selfie on Mars. So if you're interested in learning more about the rover, you can click on the link at the bottom right of the slide, and it's actually really cool. There's a 3D rover model from NASA's website, and you can actually click on the different parts and pieces and learn quite a lot about rovers. Slide, please. Regarding the role that robotics plays in space exploration, it positively impacts multiple processes and multiple stages of the overall process. They function in assembly and manufacturing of spacecraft parts or pieces. They often are involved with testing simulations performed by NASA. Some of the most significant contributions that they present for us in the field of space exploration has to do with their in-space functions. They can explore, they can gather evidence from planets, they can service other spacecraft, they can perform maintenance, and they can even perform construction in space. Another thing to mention is that they also require much less maintenance while they're in space, much less than a human would require. And this enables them to be there for longer, getting us more data, that they can analyze and classify. Their ability to withstand harsh environments makes them extremely valuable parts of space exploration. Additionally, it allows us to preserve human life, increasing safety measures. Their ability to function autonomously also positively impacts satellite operation performance. There's just a ton of uses, and they're highly valuable to the overall process, really from the context of technology. So that answers our second question. How does this relate to STEM technology? Next slide. AI's role is also massive, but it's important to note that both AI's and robotics roles often intertwine during the various stages of the process. They are both involved with each other and help us to really effectively explore space. AI are capable of hypothesizing as humans do in the scientific method. They can guess where a planet may be located in space or what might happen during a specific process of a space mission. They can organize, analyze, and classify tons of data efficiently, allowing them to simulate space environments and conditions, positively impacting spacecraft design efficiency, performance, and testing environments. In a later slide, we'll discuss how they affect the rocket landing precision. They have actually positively impacted the rocket landing precision and led to just better performance for SpaceX. Another huge way that they play a role is through navigation. They can autonomously navigate space. They can detect obstacles, map the stars, the galaxy, and just kind of hypothesize, guess, and even see where other planets may be. So how does this role relate to STEM? I would say this role definitely relates to both the mathematics and technology portions of STEM. And the reason that it relates to mathematics is because AIs use algorithms to perform these functions. Next slide. So there's a couple of different ways, methods that they use to do this. We've got deep learning. They basically can train themselves how to do things. And then seeing images allows them to aid them in detection. So that is just one of the examples. The second example is reinforcement learning. They can actually accomplish tasks, teach themselves how to accomplish a task using only the information that they have from their current experience. So trial and error. Okay, I did that, and this is what happened. Now, how do I complete the task? It's really, really fascinating. These are a couple of ways that artificial intelligence, a couple of methods that they with which they are leveraged to help us explore space. Next slide. So just a little bit of statistical data here, and it is fragmented data. So from NASA, we have a quote from Kiri Wagstaff, JPL's computer scientist, and Mars rover driver. She said automation and AI have improved the operational efficiency of Mars rovers by 10 to 20 times compared to previous manually controlled rovers is what that should say. And while this is an estimation, she's a Mars rover driver, so that's actually a very valuable estimation. And then we have SpaceX. As far as their rocket landing precision, they saw a 60% increase in successful landings. Planetary Technologies is an asteroid mining startup. They basically mine resources, extraterrestrial resources, and they estimate AI productivity, an AI productivity boost of around 75%. They can extract 75% more resources. Next slide. So this is my source page. It has a list of a lot of valuable websites. And then just to the right, a little fun tidbit. These are AI generated images from Bing Chat. And if you'd like to look at the images closer, you can scan the QR codes and get a closer look on your phone. So thank you very much for listening. I definitely appreciate it.
I want to thank the class and Miss J for viewing our presentation, and I want to thank the teammates for their hard work and dedication to this group project. I also want to give a apology for anyone viewing this live. It's made apparent that some of the pre-recorded audio for some of the slides were not playing. Hopefully, in the recording of this, everyone will be able to hear what the other members said. In conclusion, we have come so far in history when it comes to space travel exploration. We are only going to progress further in STEM feats of advancement. There is a vast area of unknown for us as a society to explore. Space, 10 out of 10. See you in the stars.